Have you ever wondered how your phone just knows the perfect song to play next? Or how your email inbox is so good at catching spam before you even see it? Well, there's this secret language at work, and it's not about words, it's all about distance. Today, we're going to decode this hidden geometry of data and see how our devices use it to make sense of the world.
It really all comes down to one simple but incredibly powerful question. How similar are two things? I mean, that question is the engine behind pretty much everything from your movie recommendations to really complex medical scans. And today, we're going to unpack exactly how it all works. So, to really get a handle on that big question about similarity, we have to start with the core idea that makes everything else even possible. Okay, so the secret sauce here has two main ingredients. First, you need a map, which data scientists call feature space. And second, you need the tools to navigate that map, and those are called distance metrics. So what in the world is this feature space? It sounds really complex, I know, but at its heart, it's actually a beautifully simple idea. It's all about turning information into a map that we can actually explore. It all kicks off with something called a feature. And don't worry, it's not complicated. A feature is just any measurable property of a thing. You know, think about describing a house. You'd use features, right? Like its square footage or how many bedrooms it has, or maybe how old it is. Those are its features. All right, now if we take those features and we just list them out as numbers, we create something called a vector. Think of it like a set of coordinates, a totally unique digital fingerprint for that one specific house. And this is where it gets really cool. Each one of those vectors, every single house, becomes one single point on a giant, multi-dimensional map. And that map is our feature space. All of a sudden, this abstract data has a physical location, a geometry. And of course, once things have a location, we can start to measure the distance between them. Which, you guessed it, brings us to our tools. If feature space is the map, then distance metrics are the rulers we use to measure everything on it. And just like in a real workshop, you need different kinds of rulers for different kinds of jobs. Let's look at two of the most fundamental ways to measure distance. On the left, you've got Euclidean distance. You definitely learned this in school. It's just the straight line, as the crow flies, the shortest path from A to B. But on the right, we have Manhattan distance. This is more like how you'd actually navigate a city. You can't just cut through buildings, right? You have to walk the grid, block by block. And this method is actually often more robust when you have a ton of features, because one weird outlier won't throw off the whole measurement as much. But wait a minute, what if the raw distance isn't what matters most? This is where cosine similarity comes in, and it's a total game changer. It doesn't measure the distance between 2 points, but the angle between them. It's asking a different question. Are these two things pointing in the same general direction? This is absolutely perfect for things like comparing documents. I mean, two articles might have different lengths, but if they're about the same topic, their vectors are going to point in a very similar direction. So, the crucial takeaway here, the thing you got to remember, is that you have to choose the right ruler for the job. It is not one size fits all. For simple, clean data, Euclidean is great. But if you're wrestling with high-dimensional text data, Manhattan is often a better bet. If you want to find similar taste or topics, cosine is your best friend. And for binary data like comparing DNA sequences, you've got a super specific tool called Hamming distance. Now, this all sounds great when we're talking 2 or 3 dimensions, things we can actually picture in our heads. But what happens when our map has thousands or even millions of dimensions? Well, that's when things start to get a little weird. Welcome to what's known as the curse of dimensionality. In these unbelievably vast spaces, a really strange thing happens. Everything starts to seem equally far away for everything else. That contrast between near and far just kind of vanishes, and our standard rulers, they become way less reliable. It's like trying to navigate in a thick fog. This is a huge challenge in the field, and it's why data scientists have developed all these clever techniques to try and cut through the noise. Okay, so even with crazy sounding challenges like the cursive dimensionality, these concepts are the absolute bedrock of the technology we use every single day. Let's just look at a few quick examples. You know that streaming service that just seems to get you? Well, it's plotting you as a point in taste space, and then finding other users or movies that are just a short distance away from you on the map. And your spam filter? It's measuring the distance of an incoming email's vector to the vectors of thousands of known spam messages. If it gets too close, boom, it gets flagged. When you type a query into a search engine, that query is instantly converted into a vector. The engine then races to find all the web pages whose vectors are closest to yours. And your bank's fraud detection? It's constantly mapping your purchases. If a new transaction suddenly appears as a point that's extremely far away from your usual cluster of spending habits, it raises a big red flag. Which brings us to what I think is the most important idea to take away from all of this. I love this quote. Feature space is not merely a mathematical abstraction, it is a landscape. By using these metrics, we're not just crunchy numbers. No, we're actually creating a map with its own unique geography, its own mountains and valleys that reveals the hidden structure of all that information. So the next time your phone suggests a song or autocorrects a word you're typing, just take a second to think about that invisible geometry that's at play. What kind of ruler do you think it just used? Was it a straight line, a city block, or was it just measuring the angle? The answer to that question is literally shaping your digital world.